Hello everyone. In the previous session, we learned how to evaluate a double integral by changing the order of integration. Now, in this session, we are going to learn how to evaluate a double integral by changing into polar coordinates. So, what are polar coordinates? So, we can express x and y in terms of r and theta. That is, if we have a function of x comma y, then it is called a Cartesian form. If we have a function of r and theta, then we call it as a polar form. We can represent a Cartesian form to polar form. So, we know the standard formula for that. That is, we know that x equal to r cos theta and y equal to r sin theta represents the polar form of x and y, where what is our r? R is given by x square plus y square is always equal to r square, and theta is given by tan inverse of y by x. So, we are going to use the polar form in evaluating a double integral. So why we are using a polar form, or why we are going to evaluate using by changing into polar coordinate, why not by the changing the order of integration means, this method is useful when we have, or if we have a terms like x square plus y square has a function of f of x comma y. If we have a function of x comma y in place of function of x comma y, the terms of the form x square plus y square, we are going to use this method. And also in the limit place, if we have a terms like root of a square minus x square and root of a square minus y square, etc. If we have these type of terms in a limit place, then we are going to use the polar form. If we have these terms in a limit place and in a function place, if we use the polar form, it will be easy to evaluate a double integral. So, that is why we change the given Cartesian form to a polar form, so that it is easy to evaluate a double integral. And also, if we consider x equal to r cos theta and y equal to r sin theta, our dx dy will change us to r dr d theta. That will change us to r into dr into d theta. So, if I represent, or if we have a Cartesian form double integral like this, that is double integral of f of x y, x comma y dx dy over the given region R, that can be replaced by double integral of f of function of r and theta, that is a polar form, r dr d theta over the region R. Of course, the given double integral limit x and y will change us to the limits of r and theta. Now let us solve the problem on double integral by changing that into a polar coordinate. Of course, they specify evaluate by changing into polar coordinates. So, first problem, evaluate double integral e power minus of x square plus y square dx dy, where the limits are given by 0 to infinity and 0 to infinity, by changing into polar coordinates. So, how to evaluate this? So, consider the given limits, or given double integral is double integral e power minus of x square plus y square dx dy. Limits are 0 to infinity, 0 to infinity. So, as I explained you, we have x square plus y square in a function place. So, if I apply if I change the Cartesian to polar form, it will be easy to evaluate the given double integral. So, that is, first before going to change, what are the given limits? We know that we have dx here. So, x varies from 0 to infinity and then y varies from 0 to infinity. So we know that x equal to r cos theta and y equal to r sin theta is the polar form and also we know x square plus y square equal to r square. But the given limits are, and theta is, of course, theta is tan inverse y by x, right. So, given x varies from 0 to infinity, 0 to infinity, and y varies from 0 to infinity. So, these two together, if I represent in x square or r square equal to x square plus y square, that gives you r varies from 0 to infinity. If I put x equal to 0 and y equal to 0, your r is 0. If I replace theta by r by, if I replace x and y by infinity, we have r equal to infinity. Therefore, r varies from 0 to infinity. Next, to get the limit of theta, we have theta equal to tan inverse y by x. So, if y equal to 0, tan inverse 0 is 0, and if y equal to 0 and y equal to infinity, we have theta equal to tan inverse of 0 and tan inverse infinity. Therefore, theta varies from tan inverse 0 is 0 to tan inverse infinity is pi by 2. So, theta varies from 0 to pi by 2. So, r and theta are the new limits, and also we know that dx dy can be replaced by r into dr into d theta, which is a standard result. Therefore, consider the given double integral e to the power of minus of x square plus y square dx dy between the limit 0 to infinity can be replaced by double integral 0 to pi by 2 and 0 to infinity e to the power of minus x square plus y square can be replaced by r square we have, and dx dy is r dr d theta. Now, look at the limits of r and theta. We know that this is the limit of r and this is our limit of theta. So, limit of r and theta are constant limits. We do not have a variable limit. So, I can split the integral as a line integral, that is integral 0 to pi by 2 d theta into integral 0 to infinity e power minus r square r dr. So, the first one, that is integral of d theta, will be theta between the limit 0 to pi by 2. But the second one I can't integrate directly, because in a power place we have r square, e power r square we have. So, we should replace that r square by some other variable, that is substitute or put r square equal to t, so that the derivative is 2r into dr is dt, or I can replace r dr by dt by 2, right. And also we have to change the limit. If r is 0, t is also 0. If r is infinity, t is infinity. So, I can replace this by t varies from 0 to infinity e power minus t into dt by 2. So, r dr can be replaced by dt by 2. Or if I apply the limit for this, upper limit pi by 2, lower limit 0 equal to or minus 0 into 1 by 2 times of e power minus t. Now, I can integrate e power minus t. E power minus t integration e power minus t by minus 1 between the limit 0 to infinity, or we remains with pi by 2 into minus 1 by 2 times of e power minus infinity e power minus 0, or it is nothing but pi by 2 into e power minus infinity is 0, e power 0 is 1, therefore minus of minus plus 1 by 2. So, the final answer is pi by 4. So, the final result of the given double integral is pi by 4. Problem: evaluate double integral of y square into root of x square plus y square dx dy between the limit 0 to a and 0 to root of a square minus x square by changing into polar coordinates. So now in the given problem, in a function place f of x comma y place we have x square plus y square, and also in a limit place we have root of x, a square minus x square. Therefore, if I change that into a polar coordinates, I can easily evaluate. So consider the given double integral y square root of x square plus y square dx dy between the limit 0 to a and 0 to root of a square minus x square. So now we should know what is the limit of x and y, right? So they given dx dy, I write it in the same order, but I can't write that because in a limit place we have x square root of a square minus x square. Whenever we have a x in a limit place, then that should be the limit of y variable. Therefore, this should be dy and this should be dx, right? So y varies from 0 to root of a square minus x square and x varies from 0 to a. That is, given x varies from 0 to a and y varies from 0 to root of a square minus x square. That is, y equal to 0 and y equal to root of a square minus x square, or I can write this as y square equal to a square minus x square, or we have x square plus y square equal to a square. That is the given curve. That is nothing but a circle with center at origin and radius equal to a, right? So let me represent that curve before going to convert that into a polar form. So we have a circle with center at origin 0, 0 and radius equal to a, okay. So now we know that x equal to r cos theta and y equal to r sin theta is the polar form, and of course x square plus y square equal to r square, and theta is given by tan inverse y by x, and of course we should remember this dx dy must be equal to r dr d theta. So to find the limit of r and theta, we have x square plus y square equal to a square, but we know that, so given x square plus y square equal to a square, but we consider r square, that is x square plus y square as r square, therefore r square equal to a square, which implies r equal to a, right? First condition. Another condition, both x and y varies from 0, it starts from 0, therefore your r varies from 0 to a. So if I replace here x equal to 0 and y equal to 0, we will get r equal to 0. So r varies from 0 to a. Next, to obtain the theta limit, so from the figure we have both x and y varies from 0, that means it starts from here. So y varies from 0 to the y axis, that is nothing but pi by 2. Therefore, theta varies from 0 to pi by 2 only. Therefore, theta varies from 0 to pi by 2. Now consider the given double integral of y square root of x square plus y square dy dx between the limit 0 to a and 0 to root of a square minus x square is nothing but double integral. So we know what is y is given by r sin theta. So if I square that, we have r square sin square theta into root of x square plus y square. So we know that x square plus y square is r square if I replace that, so that we have root of r square into dx dy is r dr d theta, where theta varies from 0 to pi by 2 and r varies from 0 to a. Now simplify and then integrate with respect to r and theta, that is given double integral reduces to. So again, so now we have r and theta has a constant limit, we do not have variable limit. So I can separate r and theta, that is integral 0 to pi by 2 sin square theta d theta into align integral 0 to a square root of r square is r into r square will be r to the power of 4 into dr. So r varies from 0 to a, theta varies from 0 to pi by 2. So I can apply this whenever we have both the limit as a constant limit, not with a variable limit. So first, for the first part, since the limit is between 0 to pi by 2, we can apply the standard reduction formula, and the formula is given by integral of sin n theta d theta between the limit 0 to pi by 2 is given by n minus 1, n minus 3 into etc. whole divided by n into n minus 2 into etc. into 1 by 2 into pi by 2 when n is even. So in this case we have even number, that is n equal to 2. So I can use the same formula, that is given by n is 2, therefore we have 2 minus 1 by 2, that we have a last term, into the constant, that is pi by 2, right, into that part is first line integral is over. Second part is integral of r to the power of 4, that is r to the power of 5 by 5 between the limit 0 to a. So we have pi by 4 into 1 by 5 into a to the power of 5 minus 0 is nothing but a power 5 into pi by 4 into 5 will be 20. Evaluated result of the given double integral by changing into polar coordinate is pi into a to the power of 5 by 20. Now the next problem is evaluate double integral root of x square plus y square dy dx between the limit minus a to a and 0 to root of a square minus x square by changing into polar coordinates. So now again in the given problem, in a function place we have x square plus y square, and in a limit place we have root of a square minus x square. So I can easily evaluate if I change that into a polar coordinates, right. So consider the given double integral root of x square plus y square dy dx between the limit minus a to a and 0 to root of a square minus x square. So since I have x in a limit place, of course this should be the limit of y varies from 0 to root of a square minus x square, and then x varies from minus a to a. So the given limits are x varies from minus a to a and y varies from 0 to root of a square minus x square. That is y equal to 0 and y equal to root of a square minus x square, or y square equal to a square minus x square, or we have again x square plus y square equal to a square. Now to find the limit of r and theta, let me represent the given curve first. So again we have a circle, right. So the given equation is a circle with center at origin and radius equal to a. Okay. And also we have another condition, that is x varies from minus a to a. So this is the value of x. X varies from minus a, that will be the line x equal to minus a, and this is our line x equal to a. Okay. Now to find the limit of r and theta, it is clear that we have x square plus y square equal to a square, right? And we know that the polar form, we know this polar form, that is x equal to r cos theta and y equal to r sin theta, and also we know that x square plus y square is r square and theta is tan inverse y by x, and of course we should write what is dx dy. Dx and dy is r dr d theta. Since we have x square plus y square equal to r square and x square plus y square equal to a square, that implies that r varies from 0 to a. So the limit of r is between 0 to a. Next, to find the limit of theta, we have y equal to 0, the given limit, and we know that y equal to r sin theta. If I equate that to 0, we know that r is 0 and also sin theta is 0 now, right? So r theta equal to sin inverse of 0, because we know that our angle, we are going to measure the angle which start from x axis, right, where x axis equation is y equal to 0, that is why we consider y equal to 0 there. So from this we are getting theta has sin inverse of 0, right, and we know that sin inverse of 0 is equal to 0, and sin inverse of 0 we have one more value, that may be pi, right. So our theta limit is 0 to pi, therefore theta varies from 0 to pi. Since why we consider that? Because the given bounded region is this part at x equal to minus a to a, therefore your theta varies from 0 to pi. Now consider the given double integral. Double integral root of x square plus y square dy dx between the limit minus a to a and 0 to root of a square minus x square, that can be changed to polar form, that is double integral. A root of x square plus y square can be replaced by root r square, and dy dx is nothing but r dr d theta, where theta varies between 0 to pi and r varies from 0 to a. So again we have a constant limit, we can split the integral, that is integral 0 to pi d theta into integral r root of r square will be r into r will be r square dr between the limit 0 to a. So theta varies from 0 to pi, r varies from 0 to a. I can evaluate integral of d theta is theta between 0 to pi and r square integration r cube by 3 between the limit 0 to a. So upper limit pi, lower limit 0, 1 by 3 common, upper limit a minus lower limit 0. So your answer is pi into a cube by 3 is the required result. So next problem, evaluate double integral sin pi into x square plus y square dx dy over the region x square plus y square less than or equal to 1 by changing into polar coordinates. Okay. So what is the given double integral? Given double integral is sin of pi into x square plus y square dx dy over the region R. I represent it as R, where what is R? Where R is a circle x square plus y square equal to 1. So we are supposed to evaluate the given double integral over the circle x square plus y square equal to 1. That means a circle with center at origin and radius equal to 1 unit. So that will be like this. So we are supposed to evaluate the given double integral over this. So we have to evaluate over the whole circle because we don't have any other limit. In the previous problems, we have x limit as 0 to a and y limit as 0 to root of a square minus x square and so on. So in that we specify whether we have to evaluate in the first coordinate or in a first two coordinates. But here we don't have a limit of x and y separately. We are supposed to evaluate over the given region, and that region is a circle. So we have to evaluate over the whole circle. So from figure, or since we have x square plus y square equal to 1 and we know the standard polar form, the polar form is x equal to r cos theta and y equal to r sin theta, and x square plus y square is equal to r square, and theta is given by tan inverse y by x, and of course dx dy is given by r dr d theta. So this is our standard known result. So from this, since they given you x square plus y square equal to 1 and we have x square plus y square equal to r square, we can conclude that r varies from origin to the circumference of the circle with 1 unit, that is the radius equal to 1. And theta, of course we are supposed to evaluate over the whole region. That means the given region is a circle. So what is the angle of the circle? Yes, the angle of a circle is 2 pi. So theta varies from 0 to 2 pi. So consider the given double integral sin pi of x square plus y square dx dy over the region R. I represent it by R because R is given by x square plus y square equal to 1. Of course less than or equal to 1. That is nothing but integral of sin pi into, this can be replaced by, change that Cartesian to polar, x square plus y square can be replaced by r square, and dx dy is r dr d theta, where theta varies from 0 to 2 pi and r varies from 0 to 1. So again here also I can split the double integral as a multiple of line integral because yes, both the limits are constant limit, that is integral 0 to 2 pi d theta into integral sin pi r square r into dr, where r varies from 0 to 1. I can integrate the first limit directly, but what about the second one? I can't integrate the second one directly because in angle place we have r square. That should be replaced by some other variable. I substitute that as t. Put r square equal to t, so that 2r into dr is dt, or we can replace r dr by dt by 2. Of course we should get the limit of t now. If r is 0, because the lower limit is 0, our t is 0. If I put r is 0 here, then you will get t as 0. If r is 1, t value is 1. Now substitute and integrate the first one, d theta integration theta between the limit 0 to pi into integral t varies from 0 to 1 sin pi t into r dr can be replaced by dt by 2. So upper limit 2 pi, if I apply the limit for the first part, 2 pi minus 0 into 1 by 2 common, integral of sin is minus cos pi t by pi between the limit 0 to 1, or we have 2 pi into minus 1 by 2 pi common, apply the limit in place of t, substitute 1 upper limit, and in place of t lower limit is 0. So cos pi t is 1 minus cos 0. So I can cancel 2 pi and 2 pi, so that we remains with minus of cos pi minus 1, cos 0 is 1, so that minus of minus minus 1 will be minus 2, minus of minus we have plus 2. So the evaluated result is 2. The next problem, evaluate double integral x square dy dx between the limit 0 to 2a and 0 to root of 2ax minus x square. So in the limit place we have root of some number ax minus x square. So we can easily evaluate this by, yes, by changing into a polar coordinate. So consider the given double integral and let me know what is the limit of x and limit of y before going to change it into a polar coordinates, that is root 2ax minus x square. Since we have x in a limit place, that should be the limit of y variable. So y varies from 0 to root of 2ax minus x square and x varies from 0 to 2a. So given x varies from 0 to 2a and y varies from 0 to root of 2ax minus x square. That means we have y equal to 0 and y equal to root of 2ax minus x square. Whenever we have variable limit, we should simplify that, right? So that y square equal to 2ax minus x square, so that we can know what is the given curve, or x square plus y square minus 2ax is 0. Okay, or if I group these two terms, we know the method of completing the square. So if I apply that, we have a square minus 2ab. So I miss with a square, right? So I add by a square and I subtract by a square, that is x square minus 2ax plus a square minus a square plus y square is 0. Or if I group these three terms, I can write it as x minus a whole square plus y minus, I write y square as y minus 0 whole square equal to a square. Yes, we know that this represents a circle. So what is the standard equation of the circle? That is x minus h whole square plus y minus k whole square equal to r square. Yes, this is in the form x minus h whole square plus y minus k whole square equal to r square, where center is h comma k is a comma 0 and radius r is given by a. So let me represent the given circle, that is like this. So y axis, x axis, the center of the circle is a comma 0 and radius is a. So center is a comma 0 and radius is a, means it passes through the origin, right? This is our r. This is our given curve with center at a comma 0 and radius r equal to a units. So now we know the standard polar form. We have to change it into polar form now. We know that x equal to r cos theta and y equal to r sin theta, and we know x square plus y square is r square, and of course theta is tan inverse y by x. So on dx dy, yes, r dr d theta is our dx dy. Now to get the limit of r and theta, consider the given curve. The given curve is this. Now consider the given curve, that is x square plus y square equal to, I write it as equal to 2ax, and now represent your x, y in a polar form. We know that x square plus y square is r square, is 2a into your x is given by r cos theta. So I can cancel r one time, r is 2a cos theta. So r varies from 0 to 2a cos theta because we have a lower limit x and y values 0, right? Therefore r varies from 0 to 2a cos theta. So your Here x and y both are varies from 0, it starts from 0, y varies from 0, y equal to 0 means it is x axis, right, and it varies from 0 to root of some circle. So I can consider the theta value as theta varies from 0 to this pi by 2. So theta varies from 0 to pi by 2, that means we are evaluating in a first quadrant. So we know that in a first quadrant our theta is 0 to pi by 2. Therefore, consider the given double integral x square dy dx between the limit 0 to a and 0 to root of 2a x minus x square, that can be replaced by integral 0 to pi by 2 integral 0 to 2a cos theta. X square is nothing but r cos theta whole square. We should represent x in a polar form. So x is equal to r cos theta whole square. Dy dx is r dr d theta. Now, as we done in the previous problems, here we can't separate the double integral as a multiple of line integral, because one is a constant limit and another one is a variable limit. So we can't separate them, we should evaluate one by one. So keeping theta constant, integrate first with respect to r, that is integral 0 to pi by 2 will remains with cos square theta into r to the power of we left with r square into r cube integration r to the power of 4 by 4 between the limit 0 to 2a cos theta d theta, or I can take out 1 by 4 common, integral 0 to pi by 2 cos square theta into upper limit 2a whole power 4 into cos to the power of 4 theta and lower limit is 0 into d theta, or I can take out 2 power 4 into a to the power of 4 by 4 common, so that I remains with cos square into cos power 4, that is integral of cos to the power of 6 theta d theta between the limit 0 to pi by 2. So this can be simplified using our standard reduction formula, 2 to the power of 4 into a to the power of 4 by 2 square into, so n is here 6 minus 1 5 into 3 into 1. Once you got odd number in numerator, expand up to the least odd number, divide by even number 6 into 4 into 2 followed by pi by 2. So now simplify this, 2 power 4 we have, so here we have 2 power 2, 2 power 1, 2 power 1, that means 2, 3, 4, I can cancel 2 power 4 and we can cancel 3 1s are 3 2s are, so the remaining result is 5 times of pi into a to the power of 4 by 2 power 2, 2 power 1 is nothing but 2 cube is 8. So the required result is 5 times of 5 pi a to the power of 4 by 8.